The mass of a star, just like the mass of anything else, can be determined by looking at nearby objects, right? Newton's laws of gravity. Just how Neptune was discovered, right? He looked at Uranus and went, something's wrong. So the mass of the star can actually use Newton's law of gravity to figure out how big it is and what's going on with it. Now, most stars are not by themselves like our sun. Most stars are in multiple star systems. Binary is a big one. Two stars going around the same center of mass, okay, gravitationally attracted to each other. So we have to classify these binary stars because we classify everything else, right? So first classification is pretty darn easy. Visual binaries. Basically, here's star 1, here's star 2, you can see them, therefore they're visual. And so you can kind of see them in the picture here. Star 1, star 2, you see star 2 is a little bit smaller. Another type is spectroscopic binaries. Now these guys are very far away. If you just look at the light, like if you're standing on Earth looking at them via naked eye, if you can see them, binocular, telescope, whatever, and you can just see what looks like to be one dot in the sky. Well, you can't tell them apart visually, so what do? You look for the Doppler shifts and the absorption lines. And you'll see these absorption lines kind of shift, right? And, well, absorption lines don't shift. They are what they are because of composition and temperature. So if they're shifting, then you must be looking at two different objects. And so that's what the absorption lines tell you. Now the Doppler will tell you shifting away, shifting towards, right? Red shift, blue shift. And so you might be able to see that as well. So the shifting in the spectral lines, right? They look like it's only coming from one star. However, it's varying over time, right? You look at it now, and then you look at it in 3 months, and you look at it another 3 months, and they're changing. Well, they shouldn't change, right? So it implies that there's two stars there. Sometimes you're lucky enough and you actually do get two completely different spectral lines. And if you do that, then obviously you know there's two different things there. The last classification, eclipsing binaries. So again, sometimes you can't really tell that there's two there, but one star will move in front of the other. And when that happens, the brightness that you're going to see, the apparent brightness, will drop because one's blocking the other one. And so depending on if the big star's in front or the little star's in front, you're going to have a bigger drop or not so much of a drop. Right. So this is what this is showing. The intensity or the brightness, if you will, and then the drop over time as one star is moving in front of the other. This is actually one way that we can use to find exoplanets as well. The planet goes in front of the star, and so the star brightness will drop. So we can find the orbital period of the stars. So basically how long it takes for the stars to go around each other, right, of binary stars. We can look at the spectral lines, and then if we're lucky enough to have a visual binary, we can actually see the masses. You can determine the masses. All right, so if we want to get information from a spectroscopic binary star system, we're going to be really limited. We can get velocities, but only the radial, right? So if we're trying to do the whole Pythagorean theorem thing, right, we can only get one leg. Well, that's not really that useful. All right. If we have the two-line system, the two-line spectroscopy system where we can see, okay, this is clearly one star and clearly another star, then we can get the mass, kind of the stars. If we think the star could be, let's say the star is 4 stellar units, stellar masses. But because of the range, we can really only say, well, it's 2 stellar, at least 2 stellar, when in reality it's 4. Right, so we can only get the lower end of it. Now, if we don't even have that double line, if we only have the single where we can just see the shifting of it, well, then we get even less information. All we can get is the relationship between the two stars, mass-wise. So we can say, well, this one's the bigger star, and this one's the smaller star. What that means number-wise, no idea. All right, now if they're eclipsing, then we can get a little bit more. All right, we can get the masses of both of them and the relationship between them. So this is just a chart from your textbook telling you kind of what we can apply, where this to read it in the book if you're more interested in the details of that, what we can get from each different type of star property. And back to the HR diagram, right? Now this will give us the mass. It's an amazing graph, right? So if it's along the main sequence, it can give us the mass. If it's lower than the sun, right? So the sun is 1 stellar mass. If it's lower than the sun, it's going to be less massive. If it's higher than the sun, it's going to be more massive. So hotter stars, more massive, cooler stars, less massive. All right, so here you can see basically red dwarfs and dwarfs in general are the biggest portion of the stars, and then the giants are the smaller portion of the stars. Okay, so not the HR diagram, right? This is actually radius versus mass and luminosity versus mass. And you'll notice the sun is at 1 because it's solar units. So the sun is 1 for everything. But basically this says as the mass increases, so does the brightness. That's all it's saying. So this is another table from your book. Gives you some stars, classifications, blah, blah, blah. But it's basically showing you here that the temperature and the luminosity will go down if the mass goes down. Now what's interesting here is that the lifetime increases as the mass decreases. So the life of the star is longer if the star is not very massive. Kind of like a car, right? So if you're looking to buy a car and you want the gasoline to last you a long time, right? One tank to last you a while, so you want good mileage is what I'm saying. Are you going to look at the Corvette or the Cruise? Right? Obviously, you're going to be looking at the Cruise rather than the Vet. Everyone looks at the Vet, but not for gas mileage, right? If you want gas mileage, you want the little car. It can go further on one tank of gas than the Corvette. It's going to eat up more. So the fancier, the bigger it is, the more gas or the less distance you're going to get on the gas. Make sense? So the smaller the car, the longer distance you're going to get on one tank. This is what it's saying with stars. The smaller the star, the longer that star is going to last. So our sun is in the middle. Our sun should last 10 billion years. It's pretty much around 4.5 right now. So we're, midlife crisis of the sun. All right, so remember, smaller car, gas can take you further, or one tank can take you further. This is what this slide is saying, essentially. The larger mass stars use their fuel much faster. Lower mass stars have a longer life. They don't use their fuel as fast. Okay, so again, putt-putt versus Corvette. Now, in the next chapter, which we're actually going to be able to do, is what happens in the star's lifetime. So, okay, I get it. Smaller stars, longer lifetime, but what does that lifetime entail? And that's chapter 11.